Welcome to the last section in Chapter 8 and in this unit. Today we're going to talk about the potential energy graphs and how they're related to force and change in energy and the stuff like this. We're going to start with stuff that you already know and then get to something that we haven't learned yet. Imagine that we've got some object, some ball, and it's going to be falling. As it's falling, it's losing gravitational potential energy, but it's gaining kinetic energy, right? And so the change in the kinetic energy is equal to the change in the potential energy. Right? So if this, but this is gaining and this is losing, so this is going to be a negative. Right? Another way to think of it is that if we're not talking about potential energy, but thinking of gravity as an external force, that force is doing work on this object. So the change in the work done by gravity is equal to the change in the kinetic energy. But the work done by gravity is equal to the negative change in potential energy. Right? So work done by gravity is equal to the negative change in potential energy. Right? As gravity does more work, think of it that way, then it loses potential energy. Right? It's losing the potential energy that it has because of that force, because of the gravitational force. Okay, and so how do we calculate work? Well, work is integral f dot dx, right? And that's equal to negative of the total change in potential energy. So we end up with then the negative, the change in potential energy is the negative integral of that force dot product with dx. It's like we're adding up all the little works that are done over time as this thing goes down. Here it's a constant force, so we don't need the calculus, but we will need the calculus later. This is going to come in again and again and again. Don't forget your units. Your units here are important for thinking about what this relationship is. What is potential energy? Potential energy is in terms of joules. What is a joule? It's a Newton times a meter. So if I want potential energy, how do I get that from these units? I'm multiplying. And what is like multiplying? Integration. Right, and then we can go the other way. If we rearrange this, I see, oh look, this is a dx. If I divide this over to this side, right, watch what happens. That the force is equal to negative du dx. If I have some function that expresses the potential energy as a function of position, not as a function of time, but as a function of position, I can take the negative derivative of that, and that gives me the force on that object as a function of position. Okay, so what does that mean? We've got this graph in the fourth slide of this presentation, and it looks something like this. It's the top graph is potential energy, and it looks kind of like this, right? And then this is the force graph, right? Remember, force is the negative derivative. So the derivative of this is 0. And here the derivative is negative. And it's increasing. It's reaching some high point around here. This is negative, so this is going to be positive, right? So I'm going to put a high point around here. And then it's going to 0. So at this point, right, the derivative here is 0. So this is going to be coming down like that. And then reaching, this is a large positive slope. So I'm going to make it a large negative, right, a negative value. That's the low point there. And then again, 0 at this point. So this is 0 slope. If this is negative, the derivative of this, right, this is potential energy, this is force. And so now again, it's at the steepest here. So at this steepest point, that's where it's going to be at some high point. And then again, 0. And then some steep, this is steep and positive, so this is going to be down negative. And at this point, it'll be back to 0. Right? So then the force graph looks something like that. Okay? And this should reach that point. Okay. Again, it might be a little bit confusing thinking about the negative derivative, but it works. It works in terms of the math and the calculus, and we're going to be using this again and again. Right now, we're actually starting pretty simple. So then we've got another example right, using calculus relationships now. So we're given a function. Here's the function of the potential energy as a function of position. So it's 2x plus 3x squared. And so we want to know the force applied. What is the F, the force at 3 meters? All right. So first of all, let's take a look at, let's do what we know how to do. Take the derivative, and we'll make it negative, and then we'll plug the numbers in, right? So negative du dx is what the force is. And so the negative derivative of this is going to be negative 2 minus 6x. Right? So then F at 3 is going to be negative 2 minus 6 times 3, which is 18. So we're going to end up with what? Negative 20 newtons. Okay. And we've got these graphs here so we can see what do the graphs look like, how are these related to each other. And we have these functions, this and this. Here, if we factor out x, then we get 2 plus 3x. And so our zeros for this are negative 2/3 and 0. So for the potential energy graph, I've got 0 and negative 2/3. And so this is going to look like this. And then for the force graph, here I've got a y-intercept of negative 2 and a slope of negative 6. So 1, 2, that's like that. And then this is going to be reaching 0 around 1/3 or so. Negative 1/3, this is negative 2, and it's linear. So it looks like that. This is the negative derivative of that function. Okay. So next one, using calculation relationships, B. Now we're given the function as force. So Fr is 2r plus 3r squared. It's the same as before, except now we've got, now it's force and not potential energy. And so now we want to know what is the change in potential energy. So delta U from 1 to 3 meters. Okay, so the change in potential energy is the negative integral of F dot, in this case, dr. And so we're going to take the negative integral of 2r plus 3r squared dr. Let me come back over here. So this is going to be negative r squared minus r cubed. That's it. And now we're going to be going now, this is a definite integral from 1 to 3. So I plug in my numbers here. And do we have any shortcuts? Nope. So negative 3 squared minus 3 to the third power. And then minus, so plus 1 plus 1. So this is negative 9 minus 27 plus 2. So negative 36. So negative 34 joules. All right. And then what do these graphs look like? Well, again, this one is like the graph that we had before. It's going to be like this. Force, this is going to be 0 and negative 2/3. And then this graph, if we take a look at it, it's third order and it's negative, so it's going to be going down like that. Okay. Okay. So what we can do is we can find that the force that a particle feels at a given position on a potential energy curve, right? Again, F is the negative slope of the tangent line. And by looking at potential energy graphs, we can also figure out how much kinetic energy there is if we're told how much total energy there is in the system. All right, so take a look at example 1, where it's got that big graph thing next to it. Right, so it's a 2 kilogram body in one-dimensional motion. So it's moving along a single path, so up and down or left and right, due to a conservative force that does work on it. So there's some force, it's conservative, so it's part of the system, and it's adding to or taking away from the potential energy in the system, and so contributing to the kinetic energy as well. The total mechanical energy is limited to 7 joules. Now if I look at where 7 joules is, that's above. So at time 0, or rather position 0, I have 6 joules of potential energy, but if there's a total of 7, that means I've got 1 joule of kinetic energy at position 0. You see how it's just the difference between whatever the value is on the potential energy graph and how much total energy there is. Okay. So for this example, in 1, it says find the kinetic energy of the body at 4 meters. If you look at 4 meters, it's at, it has 0 joules of gravitational potential energy. And so since E total is 7, it's going to have 7 joules of potential energy. For 2, it says find the kinetic energy of the body at 7 meters. So you look at 7 meters, it's at 3. The total, so at 3, at 7 meters, you can see it's got 3 joules of potential energy. That means it's got to have 4 joules of kinetic energy. All right, and then at 9 meters, you look at where 9 is, it's got 1 joule of potential energy. That means it's got to have 6 joules. 6 joules of kinetic energy. And then at 12 meters, it's got 4 joules of potential energy, which means it's got 3 joules of kinetic energy. And it says find the speed of the body at 12 meters. Well, so it's got 3 joules of kinetic energy. So K is 1/2 mv squared. It's a 2 kilogram object. This is 3. So 3 joules is equal to 1/2. It's a 2 kilogram object. V squared. Those cancel out. So it's a square root of 3 meters per second is the velocity. All right. Now the next one, this is different because now we're limited to having only 5 joules. If you read it, total mechanical energy is limited to 5 joules. What it means then is that this object, whatever it is, can't get past about 2 meters. It'll never go to the position 0. You can think of this just like a roller coaster. Right? However much energy it has at the beginning, and then it's transferring from kinetic to potential. But here, if it's limited to having only 5 joules of energy, total energy, that means it can't have 6 joules of potential energy. At position 2 or so, right, 2 meters, it's all potential energy, it has no kinetic energy. And it'll never get above that point on the graph. It'll never go all the way to position 0. So these are going to change. Since we're limited to 5 joules, it says find the kinetic energy of the body at 4. Well, 4 has 0 potential, so it's got to be 5 joules. The maximum is all kinetic energy. Right? At 2, find the kinetic. At 7, it has 3 joules, so there are only 2 joules left for kinetic energy. And then 3, the kinetic energy at 9 meters, it's only got 1, so the rest is going to be kinetic, 4 joules. And then at 12 meters, it's 4 joules of potential, so it's 1 joule of kinetic energy. And then the speed, it says, will the body ever be found at 2 meters? Yes, it can be found at 2 meters, but it'll be at 2 meters with no kinetic energy. It'll all be in the form of potential energies. That's like reaching the high point, a ball thrown up into the air. That's not what this is, because this one, the amount of potential energy changes. There's some other forces going on here, right? Maybe some electromagnetic stuff. Okay, so now, example 3, we're given the potential energy versus position graph for 2 kilogram body, but now we're limited to 3 joules. Right? And so the kinetic energy of the body at 4 meters, well, it's 0 joules of potential energy there, so that means all of it, 3 joules, is in the form of kinetic energy. At 7 meters, it's got 3 joules of potential energy. Since it has 3 joules of potential energy, it has 0 joules of kinetic energy. And then the kinetic energy at 9 meters, it's only 1 joule of potential energy, so we've got 2 joules there. And then it says, what can the body ever get to 2 meters? Can it ever get to 12 meters? The answer for those two is no, not enough total energy. It only has enough energy in the system to get up to, on the graph at least, up to 3 joules of energy. Okay. So now we're talking about equilibrium. Equilibrium is a point where a particle does not move even for an instant. So, for example, like on this graph that you see here, if it was something like that, not quite, this is a point of equilibrium. If you put like a marble here or something like that, if you push it this way, it'll come back this way. If you push it that way, it'll come back this way, right? Also here, if you put a marble there, that's a point of equilibrium. Points of equilibrium are places where the slope is 0, where the tangent line has a slope of 0, where the derivative is 0. So that would be like that, that. If this is a horizontal line, it's also like that. Okay, and then this is stable equilibrium. Stable equilibrium is if you push it to the left or right, the force will push it back, right? It'll push it back to that position. Here, if you push it to the left or right, the force will then push it away from that position. And then, so stable, unstable, this is neutral. Neutral equilibrium, if we push it, the amount of force is not changing. The force pushing to the left or right is still 0. Because here, if I push this to the right, the force is going to be to the left. Why? Because this is going up, but the negative derivative is going to have a negative value, meaning the force will be pointing in the negative direction. If I push this to the left, right, it's sloping downward. Since it's sloping downward, the negative derivative is going to be positive. So if I push it this way, the force is in the positive direction. So it gets pushed back. That's kind of like this. Okay, this is a watch glass. Okay, and if I put this little marble in there, you can see the marble just stays put. That's stable equilibrium. Right? But if I turn it upside down, if I were to balance it perfectly and I had steadier hands, it would stay at that point. But then if I push it to the left or right, then it's going to continue going in that direction. So this is unstable equilibrium. This is stable equilibrium. And then if I just had a flat surface to put this on, that would be neutral equilibrium. Right? It works the same kind of way. So stability at equilibrium 1, we have an example here. This is, if we look at, from the previous example, calculus relationships B, this is the, or something like this. Potential energy is a function of time. And then force, or not as time, sorry, as a function of position. And then force as a function of position. If this is the potential energy, what does the force graph look like? So this is going down, right? So that means it's going to have it's steep, so it's going to have a high. This is going down, so it's negative. A high positive value. And it goes to 0 here, so this is going to go through 0. But it's getting less steep as time goes on, so that means it's coming down. It's going to look something like this, right? Maybe not quite that steep. So what does that mean? As I go this way, the force is negative, right? The force is negative, which means that the force is in that direction. If I pull this thing this way, as it goes this way, that means the force is positive. At this position, the force is positive, but positive force pushes in the positive direction. So this would be an example here of a place of stable equilibrium. All right. If, though, I have something like this, potential energy versus position. So here's force is a function of position. The derivative of this would look something like this. If this is a quadratic, this is a cubed function. And you can see if I go this way a little bit, so this is 0, right? 0 slope, so that's right there. But if I go this way, then notice here that the force is positive. So if I go positive direction, the force is positive, so positive force means in that direction, this is going to be pushing that way. If I move a little bit to the left of the equilibrium position, then I'm getting to a negative force value. A negative force value means that the force is pushing to the left. So if I go this way, I get pushed further that way. If I go that way, it gets pushed further that way. That's unstable equilibrium. And then neutral equilibrium, again, would be something like this, right? Straight line across. So then what's the slope of that? The slope of that is just this, 0. So as I go this way or this way, there is no horizontal force pushing it one way or the other. Okay, so here's an example, example 4, and then that's it. Okay. So u of x is 8x squared minus x to the 4th. Okay, so we want to locate the equilibrium positions for this function, describe stability, graph the potential energy function, and graph force versus displacement. Let's try to do this all with without a calculator. Okay, so since we have that, let's find the force function. And remember, force is the negative derivative, right? If you happen to forget, let's say you forget. First of all, remember that it's negative. I'm like, okay, to get the force, is that taking the derivative or taking the integral? If you're taking the integral, it's like multiplication. So if you multiply this, which is joules, by position, which is meters, joules times meters doesn't give us anything. But if I take joules and I divide by meters, and that's what derivation is, right? It's like dividing. Joules divided by meters gives me this. So, okay, it's negative du dx. That works. Joules over meters gives me newtons. That's what I'm going to use, right? So you can use the units even if you happen to forget. All right, so let's take a look at this. The derivative here is going to be 16x, negative 16x, plus 4x to the 3rd. Okay, what are the zeros of this? The places where this equals 0. Well, I can take out x squared, so then I end up with 8 minus x squared. Here I can factor out an x, so I end up with x, and I can do 4x squared minus 16. I can factor out a 4 as well, so 4x, x squared minus 4. So this is 4x, x plus 2, x minus 2. The places where I have equilibrium are the places where the slope is 0. So where's the slope 0? Where I have this, where this is 0. This is the slope. And so the places of equilibrium are going to be negative 2, 0, and 2. And now I need to figure out, are these stable or unstable equilibrium? All right. Well, let's graph this. And let's make a little table. So here's position. Let's do one for potential energy and a column for force. So we're just going to plug in our values. If I have negative 2 as x, I know this is 0, but what's negative 2 when I plug it in here? All right, so negative 2, this is going to be 8 minus 4 is 4. 4 times 4 is 16. Okay. Let's do negative 1. Go on that side. So if I put negative 1 into this, 8 minus 1 is 7. 7, so this is going to be 7. And if I put 1 into here, or negative 1 rather, negative 1, so this would be positive 16. 16 minus 4, this is going to be 12. Okay, if I put 0 in, then it's all 0. If I put 1 in, 1, this is going to be negative 16 plus force. This is going to be negative 12 for the force. For the potential energy, this is going to be 8 minus 1, so just 7 again. If I put in positive 2, this is a 0 for that one. And positive 2 put in here is going to be, oh no, that's that one. So 2 put in here, again 4 times 4, so it's going to be 16. What if I put in a 3? So I can see where this is going after 2. If I put in a 3, 3 squared is 9, but 8 minus 9 is negative 1. So this is negative 9. 3 into this, oh boy, 16 times 3 is going to be 30, 48, plus 27 times 4 is going to be 2, 108, so this is 60. Okay, so what do these graphs look like? Here's potential energy. It's all mostly positive, and then drops down, and then force versus position looks like that. So potential energy at -2, so -2, 1, 0, 2, 3, 1, 2, 1, 2, 3. So at -2, this is 16, and then at 1, it's at 7, and then 0, and then 7, and then 16 again, but then it's down at -9, right? So like that. So it looks like it's doing something like this. The force graph, I've got zeros here and here and here, and it goes positive, negative, positive. So it looks like it's doing this, positive, negative, positive, something like that. So these are the places of unstable equilibrium. This is stable. So stable equilibrium, unstable, there and there. So that's my answer. So we found the equilibrium positions, we described the stability, we graphed all the functions, and so that's it.